So today's speaker is Professor Jan-Åke Larsson. Jan-Åke is a world-leading expert on cryptography, quantum computing, and the foundations of quantum mechanics. Jan-Åke received his PhD degree in applied mathematics in the year of 2000 at Linköping University, Sweden. He then was a postdoc at Aarhus University, Denmark, before returning to Linköping. Jan-Åke is now a full professor in information coding and the head of the Department of Electrical Engineering at Linköping University. His research largely evolves around the verification of quantum protocols in computation and in cryptography. In 2015 and 2018, Jan-Åke and colleagues published now very famous papers on loophole-free evidences of Venn inequality violations. Today, we are looking forward to hearing about Jan-Åke's exciting work on the underlying resources of quantum computing. So with these words, Jan-Åke, thank you very much for joining us, and the virtual floor is yours.
Thank you very much. So the title of the talk is Quantum Computation and the Additional Degrees of Freedom in a Physical System. What you see here on the graphs is you might call it simulation of Shor's algorithm factorizing 15 using classical systems. And I will talk a bit about how to do that later on in the talk. Niklas and Christopher here are students in my group, or I should say Niklas has actually finished and left for industry, but Christopher is still working on this. Let me see if I can get this activated. Here we are. You know that quantum algorithms use qubits and quantum gates. I'm showing you this to point to certain things that we will return to later on. So you know that it's common to use spin 1/2 systems, and you make superpositions of the computational states using, well, real parameters here. Gates are unitary maps, and we typically use symbols like this from these are actually from reversible logic, classical reversible logic. The last one here doesn't exist in classical reversible logic. You know that it changes base in a quantum machine. And I'm pointing to this because this is important here. It changes bases, or you might also say it changes from one degree of freedom to another degree of freedom. And this I will return to later on. I'll point out that it's actually a basis change or a rotation. You know this, but I'll stress it because that's really important. We'll do that. And you might know that quantum algorithms, well, classical algorithms, calculate a function value and do that over and over to collect information on some global property that we want to determine for the function in question. And you need a lot of function calls. For this particular task to determine whether a function is constant or balanced, so here's a constant function. You can see all the outputs are the same value for each of the inputs. This is a balanced function. The outputs change, but half of the possible values, half of the values are 1 and the other half is 0. Your task is to, in this situation, your task is to find out whether the function is constant or balanced. And in the worst case, you need to input half of the possible values and one more to determine which case it is. So a classical machine needs exponentially many calls. If you do this search randomly, you can show that you need the constant number of calls to get a bounded error probability. A quantum machine using quantum data on the inputs and the outputs can use a specific algorithm to determine this in one function call, namely you put certain values of the data on the inputs, you put Hadamard in front, you put Hadamard after, and you make a measurement. This measurement will show you immediately in one function call if the function is constant or balanced. You know this. This is a standard example of quantum supremacy, or the quantum advantage, maybe is a more appropriate word. What I'll try to do now is to look at this from another viewpoint and to talk about what does the quantum computer do? How does this come about? The standard explanation is that the Hadamard here creates a superposition of all the possible input values. So the 0 gets mapped into a superposition of all the possible values. There should probably be a -1 here. Yeah. So from 0 to 2 to the power of n minus 1, exponentially many values. All of these are input at once. The calculation is done in parallel. So somehow in the quantum system, you actually do all the function calculations at the same time. Massive parallelism. And then these parallel results are then combined by interference to find the result up here. And what I will argue now is that this is an explanation that you've seen, but it's not the best explanation. And that's basically the argument in the talk here. It's not the best explanation. I will try to give you a different point of view that will explain this better. So I came to this interested in what is the actual resource used in quantum computing. What is it that enables this speed up here? And there are a lot of different proposed resources. Superposition interference I just talked about. You hear a lot about entanglement or non-locality, different twists of the same property. My favorite here is quantum contextuality. So this is where I entered into the thing. I thought if entanglement and non-locality is a resource for communication, quantum communication, then this is obviously the resource for computing. So we'll get back to that in a bit here. You sometimes also see the continuity of a quantum state space as a resource. You can store a lot of information, it's said, in these continuous parameters that you have in the quantum state. But what I'll try to do here is to show to you, maybe convince you, at least argue, that what you actually do here is something slightly different than all of these claim. What you do is you read and write into an additional degree of freedom of the physical systems that we use here. And you do a calculation in the additional degree of freedom inside this box here. And that's what gives you your power. So the question, I will try to show you how this is done and what is computed in some cases.
So just, Jan-Åke, I have one question in the chat. So I think if you can go back to your list of resources.
My list of resources, yes.
So we have a question in the chat, and the person asking the question says, is not some instances of entanglement plus non-locality a subset of quantum contextuality?
Yes, that's true. So what you will find is that, in my view, all of the instances of entanglement and non-locality is an example of contextuality. But when you talk about these two, what you typically assume is that you have physical separation. of at least two systems, maybe more. And then you can talk about entanglement and non-locality as effects that arise in the system. Contextuality, that's more a statement on a single system in one space location that you get quantum effects in, quite distinguished from that. So you need spatial separation here to be able to talk about that. This is why this is so good, so well adapted to communication situations, because then you have two different spatial locations. Contextuality maybe is more suitable here because the computation is made in one location. So I'd agree to the statement of the in the question.
Okay, thank you.
So, you know, I'll return to this. The standard explanation is that you get a superposition of all possible values. And if you've got a generic z here, you get a generic z in the exponent here of some transformation. So this is actually a Fourier transform, or you might say Weil-Hadamard transform, or possibly bitwise discrete Fourier transform mod 2. You do a Fourier transform on each individual qubit, so to speak, a discrete Fourier transform. But you know that a Fourier transform, what you do is you change your description. So here's a function in time. Here's the same function described in frequency. It doesn't change anything. It's just a change in your description. The actual thing, in this case, the wave function, you could discuss its existence or not, but I'll just leave that. The thing you're describing, the wave function, doesn't change. It's what you do is you change the basis from this vector set to that vector set. I mean, this vector here, it's one vector. It's a superposition if you write it down in the computational basis, but it's one vector and it's indexed by z, not by x. I mean, x is not visible outside the sun. So it's a basis change. And it changes between different degrees of freedom. In the picture here, time and frequency. In quantum mechanics, we're used to talking about position and momentum. In quantum computing, it's the computational basis and the phase basis. So the index z here refers to the phase basis, so to speak. So what you're actually doing here is you're changing your description. So the zero here gets you basically write information into the phase degree of freedom. So the z here is a 0, but you're selecting the 0 basis element in the phase basis. So you're writing information that you have in the computational basis here into the phase degree of freedom. Likewise, the 1 gets written into the phase degree of freedom, and the quantum algorithm then performs some calculation. The gate array here performs some actions on those states. And the readout over here, that reads off information in the phase in between the U and the Hadamard here. There's information in the phase that gets written into the computational basis, and that's what you read off. It seems like a simple change of view, but it's gonna be important. At this point, you could ask questions. What exactly is calculated here? So what is the calculation that this thing does in the phase basis? You could also ask, do all quantum algorithms follow this pattern? You could ask what data is used. I mean, is it important that it's these precise data that's written in? And you could also ask, what are the requirements on the quantum system here? what are the requirements on this U to make this work, to get the output that our quantum algorithms needs to work? So let me see if I can answer some of these questions. So we can start with a simple example. Here's an identity from quantum mechanics that you know. So addition modulo 2 in the computational basis, that's a C note, a controlled note. And you might know that if you put Hadamard Fourier transforms before and after, this thing turns upside down. So apparently, if I write information into the phase basis here, and it gets added to information in the phase basis there. Somehow the input is on the bottom and the target is on the top. Information that I input here ends up being readable over here after a suitable transformation. So after the basis change, we have an addition modulo 2 in the reverse direction, in the backward direction. You know this as phase kickback. This is an exercise in Nielsen and Zhang to prove that this identity holds. So it's a well-known thing. But we can make this more general. What we'll do is use a result from classical reversible computation, and then I'll show that this is a more general feature of this kind of system. So we'll need to talk about reversibility here. A standard classical computing gate array is irreversible. You have AND gates and XOR gates and so on here. Typically, they have more inputs than outputs, but in general, it's just a reversible, an irreversible map. This causes heat dissipation from the system. You lose information from when you go from X to the function value, unless it's a bijective function. But if it's not a bijective function, you lose information. That will be visible as heat. In a quantum situation, you would think of a pure state here and a mixed state there. And Landauer's principle says erasing information generates heat. Landauer studied this in the 60s and 70s. The theory told him, the principle here told him that if you make classical computers more efficient, there will be a lower bound to the efficiency given by this principle here. Erasing information generates heat. So at the time, people started looking at reversible computing. So if you build a function using reversible gate arrays, you would typically preserve your input and then add the output on a bias register, denoted Y here. So the bias register is really, it becomes a bias over here. Typically, you would set Y equals 0. You recognize this from the quantum gate array. But one should...
Sorry, Jan-Åke, I have two
Yes.
questions here on the previous slide.
Oh, on the previous slide, yes.
Yeah, so the first question is the Landauer's principle related to the resolutions of Maxwell Demon? And then the second, let's do the first question first, yeah.
Yeah, I would think so, yes. But I think it would require a too long answer to do here.
Okay,
Yeah.
fair enough. But it's the same kind of information.
It's the same kind of thing, yes.
Okay.
Yeah.
And then the second question is just, can you explain what you mean by bias a bit more?
Oh, so okay, so bias, you don't need to input 0. So typically you have a register where you write the output. And in every, I think, implementation you will have seen in quantum computing, the bias register will have a 0. When you compute the function value, it's the function value you want to on the output, nothing else. But in principle, you could write anything here. and it will just be a linear shift of the output. It's not more complicated than that. So it just works as a bias to the output.
Okay, thank you.
When you do this, it's really typically hard to write down a gate array that gives you just the input value and the output shifted with a bias. Typically what you end up with is a number of intermediate results, so-called workspace. In quantum computing, you see these as ancillary systems, ancillas that you use in the calculation. So typically, a classical machine, at least, would have 3 registers, one for the input, one for workspace, and one for the output. And the heat is generated when you delete the information in the workspace. The function output you want, and it's supposed to be a reversible function, so it's neat to preserve the inputs. But in principle, the heat is generated when you erase that. So Charlie Bennett, the same of Bennett and Brassard 84, came up with a neat trick to reset this. It's called uncomputation, often in quantum. What you do is you do the function calculation, you get some work data, you get your function value, you copy your function value to the output, and then you invert the function calculation to reset the work and the function output space, so to speak. But you still keep around a copy of the function output. So now the lowest one here is the bias register, and the 2 zeros, which really are large registers, are really workspace. So it's called Bennett's trick or uncomputation. This is what you do in a quantum machine. Typically, you reset the ancillas to some known value, and then you don't get a mixed state on the output, but you still retain the function value. So it's really common. Now, the thing is that this gate array here is actually unitarily equivalent to our desired gate array, the unitary that just calculates f and nothing more. And it might not be entirely clear from here, but if I just enclose the circuit like this with the zeros, ancillas, as being used inside the system, this is what you get. So you can agree that these two are actually equivalent as unitaries. And if we now look at the phase kickback identity, Hadamard's before and after, and just do the same sort of trick. This is basically the transformations that you use in the Deutsch-Josa algorithm that I showed you before. Hadamard's before and after, well, nothing on the output, but okay. The Hadamard is its own inverse, so I can just sandwich Hadamard's in between here to a number of pairs, and you see them in blue. They sort of fit together. If I now collect the preceding Hadamard here into the thing, you can see there's a well recognizable pattern here. These things, you can see that's a function complete with Hadamard. Here's the inverse of that, the dotted lines. So I can sort of capture what happens here. And this one turns upside down. And in the algorithm, you got this number 1 here, which is input data to the calculation that I was alluding to before. So these transformed functions, they calculate something on the output, but the number 1 here gets added into the calculation before we invert. So you copy the information from the so-called target system here into the evaluation. You know that this is a reversible function. So if there's a difference on from the output here to the input here, something will need to change on the outputs of the inverse. And by constructions, these outputs here don't change. So the information has to exit somewhere. Otherwise, it's not an invertible function. And the only available position is the top one. So that will influence the measurement here. It must influence the so-called controlled output. There's a bit of it's a complicated thing. So I can't tell you all the details here, but this is the argument. The output of the function f hat, the data here changes before you invert the function, so something must change on the output. Must influence the control output. And of course, this large construct here is equivalent to the algorithm that we're looking at. So something is calculated here that influences the output. So in the forward direction, without the Hadamard, when you write a value on top here, it will perform a calculation, the function calculation to the output. In the backward direction, a different calculation is performed. We write information into the phase, and that influences the read-off on the output from the phase. And apparently, this is the controlling register, and that's the bias register. In this situation, the bottom one is the controlling register, and the top one is the bias register, because the function output, whatever it is, gets written into that register. So you can see that it's a symmetric situation. We write something into the phase, you do a calculation in the phase, and then you read it off. Of course, you can write anything in here. So you could write a value W and a value B. And you could ask now, okay, so what calculation is going on here? So if you do this calculation, if you just do the steps, I don't want to go through the whole thing here, but what happens is that W and B influence the output in the Dolciosa algorithm. You get a delta for Z, and you get this F hat, which is the Walsh-Hadamard transform of F. And if B is 0, then the coefficient here is 0, so you just get the delta, which is what happens in the Dolciosa algorithm. If the function is constant, then this is also a delta, F hat of Z. So it's a delta in both cases.
So we have a question now.
Yes.
They're asking, what does delta mean?
It's the Kronecker delta. So if Z is the vector 0, then the function value delta is 1. And if the vector Z, the bit string Z, is non-zero, then the delta is 0. So it's the delta from, you might say, computer science, rather than the Dirac delta from physics.
Okay, thanks. And I think we have another question here. So we have a PhD student. He's writing, "Hi, Professor Jan-Åke. Why you use phase kickback and then use less Hadamard gates in the right below the output as an example?"
I'm drawing the Dolciosa algorithm as it is in the textbooks, so you don't have a Hadamard here. But in the previous, let me see if I can roll back. No, that's the wrong way. Backwards. What happened here is that let me roll back so it's visible. I added 2 of them here. So this one I need, but that one will be left over. So maybe it's just confusing that I didn't draw it like that. But when I transform that into this, there will be a Hadamard at the end. So that will still be there. But in the algorithm, we don't really care about the output here. If I want the input to remain on the output in the construct here, I would need a Hadamard here also. I'm not sure that improved the situation here, but it's really because I'm using the Deutsch algorithm in the argument. If I want this number here to remain on the output, I would need a Hadamard here also. Then this thing is completely symmetric.
So now at the moment, these two things are not exactly the same.
No. So if I put a Hadamard here, then I mean, they are not exactly the same. Here you have the function calculation. This is the quantum algorithm that reveals whether it's a balanced or constant function in the Deutsch algorithm. So it's not the same calculation. Here you calculate the function value. Here you derive a property of the function, a global property of the function. That's typically what you do in a quantum algorithm.
I think hopefully that should clarify things. Otherwise, just keep asking questions and I'll keep interrupting you, Jan-Åke.
Absolutely. So what you get is a complicated expression involving the Fourier transform. That's what I meant to say here. I mean, there's a specific function that you're calculating. In this case, it's the Walsh-Hadamard transform, the Fourier transform, bitwise Fourier transform of the function. And that's really what determines the property you're after. If you could calculate this easily, you would do that, and that would tell you the properties of the function. But the quantum algorithm reveals this value for you. But it really does calculate the transform, and you could now let me just leave that. I'll continue here. Now in the Shor algorithm, the factoring algorithm, you're doing the same thing. You're looking for a global property of the function, in this case the period of the function, a value r, so that if you add r to the x you're in, you get the same function value as in f of x. And the reason you're doing this is that the period of this function, a to the power x mod n, that will give you the factors of n. So if you can determine a period of f here, you're fine. A classical machine, well, if you use randomness, it uses exponential number of operations in the third root of n, so not quite exponential complexity of the algorithm, sub-exponential. But a quantum machine needs cubic number of operations, and that's why we say it's polynomial time, of course. The gate array looks like this, and you immediately see there's no Fourier transform here, but there are still Fourier transforms here and here. So you write your 0 into the basis, you do some calculation, and then you read off again a value from the phase basis. And the calculation looks like this, and typically people say you make a superposition of all the possible values for x, you calculate all of them in parallel, and then you superpose. So the Fourier transform, the inverse Fourier transform, yes, you superpose. So what really happens here then? Well, if you look at the frequency or the probabilities really for the different values of the readoff, you can see there are peaks, and these occur for multiples of frequency this. the number R here is the period, and the frequencies are actually multiples of 1 over 2 to the m. And you can see you can never match this unless R is a power of 2, you can match the things, but typically that's not the case. You don't have R as a power of 2. And then you don't match one of these points where you get the correct R completely, so you obtain spectral leakage, and you get an expansion like that, which is roughly equal to S over R. Spectral leakage is well known in signal processing. So there are plenty of methods to handle that, and this is the reason why the algorithm is so complicated. But you can see it's a Fourier transform, and it's a Fourier transform of f that you're calculating. So the resonances occurs in multiples of this frequency here. The input here, there's still an inverse map, and the degree of freedom that you're looking at here is associated with the eigenvectors of u. So if you could input a particular eigenvector of u here, you would only have, you would only have one of the peaks. Maybe this one here, if you select a particular eigenvalue of a particular eigenvector of the multiplication operation here. Since you can't prepare one of those eigenvectors, what you do is you do a superposition of the eigenvectors here so that you get the number 1. And if you look carefully in Nielsen and Chuang, this is precisely what they say. Here you take a superposition of the different eigenvectors belonging to different values of S. The S here tells us which eigenvector you've obtained in the expansion. So you could think of this as a random sample from the possible eigenvectors. If you could write into the basis, you could determine which S you would get as an output, but of course we can't. Constructing the eigenvector on the input here would actually require knowing in advance what the factorization is, which you don't. But you can view it the same way. If you input a random eigenvector here, you would get the corresponding read-off on the output.
So Jan-Åke, I have 2 questions here.
Yes.
So we have one question from Adrian Ionesco. He's asking, is the spectral leakage appearing at the readout stage, that is the measurement stage, by the use of a certain window function?
Yes. It's related to a window function, but it in this case it really is more the discretization of the output that is responsible for the leakage. So yes, it corresponds to a particular window function, but it's a complicated relation. Okay. If you could manage to hit the points here, S over R, exactly, you wouldn't get spectral leakage. And you can actually see that in the picture here, because one of the frequencies, the middle one here, is actually spot on to one value of S over R. And then you see you don't get spectral leakage here. Also, that applies for the 0, of course, which is also the correct eigenvalue on the grid, so to speak.
Okay, thanks. The second question is, I think, on the next slide. Can you say once more what you mean with having a superposition at the lower input? It's written 1, so how can 1 be a superposition of various things?
It's a superposition of the eigenvalues to the, it's a little complicated. I mean, this is a controlled multiplication operator. The unitary here is a controlled the control, if x is 1, a is there. If x is 0, a is not there. So you can turn on and off the multiplication. And the multiplication operator will have eigenvectors with associated eigenvalues. And the 1 here can actually be resolved into the different eigenvectors of the multiplication operator. It's not clear here, but Nielsen and Chang writes it down explicitly, so you can actually see what the different eigenvectors are and how do they sum to the number 1, the basis vector in the computational basis.
Okay.
So it really is a superposition, although you don't see it when you look at it like that.
I think that clarifies it.
Yeah,
otherwise, people should keep asking.
Yes. And at this point, when we were realizing this, we asked ourselves, is this the case in every problem that the quantum computer could solve? So what we did was we looked at the BQP complete problem. The BQP complete problem we looked at is called a Hadamard test. And it's basically, I'm not sure that I want to go through all of the details here, but you're given a particular state which is guaranteed to obey either this relation or that relation with a gap in between 1/3 and 2/3. One of them is called rejecting states, the other is accepting states, and you want to figure out, is phi a rejecting or an accepting state for Q. And you've got access to a controlled Q, and this algorithm, gate array, will tell you, is it a rejecting state or an accepting state? And what we managed to show is that phase kickback is this enabling mechanism here too. For that, you need to look into the PhD thesis of my student. We haven't transformed this into a published paper yet. But in essence, our question was, does this always happen? And the answer is yes, it always happens. And I realize I'm not going
there is a quick question here. So the question is, Q, is
Yes.
that any controlled unitary, or is it a specific one in this problem?
It's part of the problem specification. So Q, if you talk about decision problems as such, Q specifies the language, and you are supposed to take the word psi here and check whether it's in the language or not in the language. And there are also psis that aren't either, but you're guaranteed that the questions asked will be one of the two kinds.
Okay, thanks.
So Q is given to you.
Okay.
Yep. And this takes a bit longer than I was aiming for. What I want to talk, I want to really convince you that superposition is not a good explanation. So if you've got a function unitary, you're used to seeing it like this. You get x on the input and f of x on the output. And you're used to thinking all that's required is that this thing here is unitary and the function values are correct on the output. What I want to tell you is that this is not the case. The reason is that you can easily, if you have u here, you can easily construct this. You just put z gates on the entry points and the exit points of the target And if you do that, you've got this phase here in between added onto the output. But you can see it's still a unitary. The dashed thing here is still a unitary. And it also gives you the correct function output. So if you only check that you get the correct function outputs and then you're satisfied, okay, this is also a unitary that gives you the correct function output. If you start your quantum algorithm here and do the calculation after the unitary, this is the superposition that you should obtain. You should get -1 and then f of x. It's called writing the function value into the exponent or into the phase. It's phase kickback. But if you do that to the lower unitary that you thought would be acceptable, then the output is this. And you can see there's no exponent here. There's no phase kickback. So it's weird that it's the same function and both of them are unitary, but the quantum algorithm seems to give radically different outcomes. I mean, here you got the phase kickback thing that you're looking for. Here you don't. If you do the inverse here, and now I actually included H on the lower system so that I recover the sort of control in the phase. You can see you get the correct expression on the top unitary. Here, you get this. Wait a minute, this is the same data that I sent in. Apparently nothing happens. So if you do Virtuosa using this unitary, the answer will be it's a constant function. Whichever f you put in, it will always say it's a constant function. Importantly, all the possible input values are still superposed. I mean, the superposition here and there, that's the same superposition. But the lower quantum algorithm fails. You do the correct interference, but you still don't recover what you want. So if you look at the kind of framework that I was sketching, what happens here is that you write the number 1 into the phase, and you know that the Z gate here, that's an inverter on the phase. So it erases the number that I wrote in. So now there's a 0 here. So there's nothing that can influence the controlling output, the phase of the controlling output. It erases the information that you need to do the backward calculation.
I have 2 questions here, Jan-Åke.
Yeah.
The first one is by one of our PhD students, Chris Long. It might relate to something that happened on a slide back or so, but the question is, does this mean that any problem in BQP can be solved with a hidden subgroup algorithm?
No, I don't think that's the implication. But I need to think about that. We're certainly not claiming this.
Okay,
yeah,
thanks. And the second question is for the slides that come here.
yes.
The person is asking, is this related to the standard quantum erasure thought experiment?
The standard quantum eraser thought experiment. No, I don't think so. But of course, there might be a connection, but I haven't really considered this, but I don't think so off the cuff like this.
Okay, thanks.
Yeah. So we were at the point here, the phase. So the thing is that this calculation that we're doing, we now know that phase kickback enables all quantum algorithms, but that means that you need to have phase kickback in the unitary here. And that depends on phase preservation. You typically write the map like this, but it's not exactly what you mean. Implicitly here, you mean phase preservation also. So you actually mean if I have an overlap with constants c, x, y here, these will remain after I've calculated my function. And it might be unexpected, but there are unitaries, call them v, that don't preserve the phase, but give the correct function output. And there are many of them. Quantum algorithm speedup requires that the phase is 0. That gives you the correct phase kickback. You can actually write down a slightly weaker requirement here, but this is the typical requirement that you see, which is sort of implicitly, or maybe explicitly, depending on the author, required by the unitary here. So this is really, really important in your quantum computer. It's not noise. This is systematic errors, because if it's a pure state here, you get a pure state here. So it's not a random noise thing. It's a systematic error, and you need to eliminate those systematic errors to make the algorithm work. This is why I think that the superposition interference description is lacking something that you can find is better represented in this kind of explanation. You actually do a calculation, but in the backward direction. So in the forward direction, the value, function value is calculated. You can choose to do transformations before and after if you do a quantum algorithm. And if you choose to do that, then you do a different calculation backwards. Or you could argue that somehow these two are simultaneously done, which would give you an entanglement, an entangled system argument, so to speak. If you think so, then you do have parallel calculations. But in this world, it's not a multiple word thing where you do lots of different calculations on lots of different x values. You do one calculation in the forward direction and a different calculation in the phase spaces in the backward direction. So this is our argument. And now I've got, it's 4 minutes left of the hour, but we have done some classical simulations here. I don't know if I should go into that. Should I?
So how much more time would it take to wrap up the talk with that? I think I'm certainly interested in seeing it. So
it depends on the number of questions. So typically at this point, I would have spent half an hour.
Yeah.
Yeah. And I aimed for an hour, so now you get sort of the picture. I could rush through it, but that would be rushed.
So I think another 15 minutes or something like that, and then maybe I hold back on the question.
I'll do that. I'll do that then.
Yeah.
If that's okay.
Yeah, that's okay.
Good. So what we did was, we said, now let's do a simple simulation here. We take our quantum system, our qubit, and we represent that as 2 bits, the computational value in blue and the phase value in red, 2 classical bits. We extended into something we call quantum simulation logic. If you want, you can compare it to Speck-and toy theory, which is another variant of the thing. When you do measurement, what you do is you display the computational bit value and you randomize the phase bit value to do the uncertainty relation, reproduce the uncertainty relation. The phase inverter, that's an inversion of the phase. A standard inverter is an inversion of the computational basis. The Hadamard interchanges the two. And the C0, you've got explicit phase kickback. So this adheres to quantum mechanical identities almost. The thing is that these are non-contextual, and now you see the connection here. I will later on extend that so that the model becomes contextual, so that we can do more of quantum algorithms. But this is the basic description here. I'm doing this rather fast now, but let's just go into what the result is. what we found was that the Deutsch-OSA algorithm can be efficiently realized in quantum simulation logic. 1 or 2 qubit input functions, the oracles are in the Clifford group. So all the gates that I had on the last page are in the Clifford group. So we can immediately just implement whatever function you have here. We can immediately implement it. And it turns out that our simulation recovers the behavior of quantum mechanics. You can immediately see if the function is balanced or constant. The classical simulation needs 1 function call. The thing is that we found also that larger oracles for more than 3 or more bit inputs, you need the Toffoli gate, but if you just do the trivial thing, the classical Toffoli gate, it turns out that you can write down oracles that give you the same behavior, 1 function call, which is a bit mysterious. A classical simulation of something where you thought you had a quantum advantage. How is that possible? Well, honestly, the simulation might not surprise you because there are classical randomized algorithms that need constant number of function calls. So the advantage is not that big, actually. So we turn to Simon's algorithm. You've got a promise for the function. You need to find the secret bit string, a parameter of the function, find it or determine if it's non-zero. Now you can prove that a classical procedure algorithm here needs an exponential number of calls, but linearly many quantum calls. The thing is that we found that our framework also finds S in linearly many calls. There's a random phase being written into the top here. I don't have time to spend on that. But this confused us because there's a theorem that says this is impossible from Simon in 97, and it says any probabilistic Turing machine that queries the oracle no more than exponentially many times can correctly guess P of n with a large probability. And we get the quantum behavior. So now what's going on here? Well, it turns out that one of the assumptions, let me see here, the function f from bit strings to bit strings in the oracle. We don't have bit strings. We have more complicated systems. Quantum mechanics escapes this because it's from qubits to qubits. So the theorem doesn't apply. In our simulation, we have this QSL systems which contain 2 bits each. So it's not a single bit. It's not a bit string. And that's all that's needed. So what we figure is that it's the ability to read and write in this extra degree of freedom, the second bit, that enables us to escape the theorem. We don't obey the assumptions, so we're not limited by the statement of the theorem. At this point, you think, okay, let's see what happens in Shor's algorithm. Then you're not in the oracle paradigm anymore, so you need to build the oracle according to the procedure that Shor specified, which is polynomial time. So, I mean, it's possible to do in polynomial time. The oracles in the 2 preceding examples are not like that. So it turns out that you're outside the Clifford group even when you try to factor 15. We quickly found out that the classical Toffoli we used doesn't work, so we need something more advanced. That's the 3 gates that you see at the center here. When we did that, we could build a classical simulation. This is in complementary pass transistor logic. So the bits are represented in TTL levels, 0 and 5 volts. and there are gates that just do everything that you saw on the previous slides. You got Hadamard over here for the inputs. You got times 4 modulo 15 times 2 modulo 15, and the inverse Fourier transform is really 3 gates at the end because it's a 2-bit system here. Thing is that there are systematic errors now because our TOEFL isn't good enough, but they're on par with state-of-the-art experiments, so it's not that bad. However, systematic errors grow rapidly when we go to larger systems. We found this interesting, but let's move on from that. We can't do Shor's algorithm for large numbers. So at this point, what we're trying to do is look at this here. Maybe if we add contextuality, it could be that we can't do this efficiently, but we could do Shor's algorithm. Okay, so then we have a good explanation of what happens, but we can't do it efficiently. Fine, very good. It might also be that we can still not do Shor's algorithm, but the contextual behavior can be represented efficiently somehow. And this is actually what happened. We modified our model here to add contextuality, and it's rather too complicated to describe in so little time. But what do I have? 10 minutes. Oh, a little then. The state here is now a symplectic basis. These are Pauli matrices, n of them each, so 2n Hermitian Pauli matrices. Each of them are bitwise x or z or identity or y, so 2n bits. You also need a sign to represent the outcome bit values stored in each Pauli here. And I realize this is too complicated to do in a short time. I never intended it even for the 1 hour without questions. I just want to show that it's a more complicated model. That's what I want to convey. In the QSL simulation, these are single Z operators, and these are single X operators, and each of them store an associated value. So if you have a 1-bit system, this is a Z, that's an X. It's the blue bit and the red bit, so to speak. But now we generalize, so we allow for more Paulis, so to speak. They can be any now, any Pauli, and you can have strings of them. Here's an example. The 2 first are actually the stabilizers of the quantum state. So this corresponds directly to that quantum state. 0 is stabilized by Z on the first, minus, so 0 minus 1 is stabilized by minus X on the second. And this is very close to the stabilizer formalism, or as it might be a better name for it, the stabilizer state tableau representation, SSTR, by Aronson and Gottesman. So we use the transformations from the stabilizer state tableau representation, and this corresponds directly to the quantum mechanical identities. So it's much closer to actual quantum mechanics than quantum simulation logic is. In quantum simulation logic, we had something which was almost correct. Here, we're in a subset of quantum mechanics, but the identities are the quantum mechanical identities now. Measurements, basically what you do is you read off the measurement outcome from the state. So if you have a state in this description, you know what the measurement outcome would be. All of them are deterministically predicted. And there's a state update rule that handles step B here, handles contextuality, and step C the randomization for the uncertainty relation. So I've just listed the model properties here. A symplectic basis of Hermitian operators. Transformations are given by the rules in an existing model. Measurements outcomes are given or deterministic once you know the state. The update is contextual, but it ensures that if you repeat the measurement, you get the same result. If you repeat the measurement and do some commuting measurements and then the same measurement again, the outcome is conserved also. You've got the uncertainty relation as predicted by quantum mechanics. So this is an update, so to speak, an extension of previous models. Those are either non-deterministic, non-contextual, low-dimensional, or exponential in complexity. So what we did was we have a model which is quadratic in memory and time, so polynomial. And it reproduces qubit stable as a quantum mechanics, which we thought was neat. Stabilized quantum mechanics can be reproduced by a deterministic description in polynomial time and memory. And we can reproduce certain properties like the Perez-Mermin square, the canonical example of contextual behavior. I won't have time to go into that. If there are questions, I could explain more. We also looked at a recent algorithm which is not also not in the Oracle paradigm. It's an explicit thing where you have you can build your gate array in polynomial time given the matrix A here. In the problem, you can write down what the gate array is. And there is a gap between quantum and classical gate arrays, where the gate arrays are limited. Bounded fan-in means a bounded number of inputs to the gates. And the algorithm works in our new model because it's in the Clifford. I mean, all the gates are in the Clifford group, so it works. We're in the subset of quantum mechanics that we can model efficiently, which we thought also was really neat. So to conclude, quantum algorithms use a second degree of freedom for the crucial calculation. The calculation is enabled by phase kickback, but it sets hard requirements on the unitary. Not just any unitary with the correct function output is useful here. You need the correct phase kickback, phase preservation. And this is, in my mind, what makes building a quantum computer difficult. Not so much reducing noise, but getting the right unitary will be the problem, I think. What we'll be doing after this is to do some classical modeling that recovers the backward map. And we have reproduced the behavior enough so that we can do certain algorithms. And if you want to read more, these two papers here will contain quantum simulation logic and this latest contextual simulation model. Thank you very much.
Okay, thank you very much, Jan-Åke. Let's see, so if anyone still has any questions, please pop them in the chat or let us know. So I see we have a question from our PhD student, Homo Yuan, who's writing, it seems that the phase kickback algorithm depends on the original UF oracle. But for many problems, it is hard to build the oracle. Would this be a barrier for extending phase kickback algorithms to solve BQC problems?
So phase kickback is responsible for the speed up in all of these problems in BQP. So I'm not sure what the question is. Would this be a barrier for extending phase kickback algorithm? Well, if it's hard to build, that would be a problem for quantum computing, yes. Not so much. I mean, we've proved that the explanation, the description of quantum computing that we use is generally valid. If it's hard to build, so I should say I'm not particularly fond of studying oracle problems, because oracle problems they don't say anything about how hard it is to build the gate array, even for a quantum machine. So that's why shallow circuits here, which is polynomial time, the building the gate array, which this one is polynomial time, and also Shor's algorithm is polynomial time, building the gate array. So I would say those are the more interesting cases to look at. I hope that's an answer.
I think so. We have another question from Christopher Long. He's writing, is the quadratic overhead related to other standard quadratic overheads we see in, for example, amplitude amplification and going from the standard quantum limit to the Heisenberg limit?
I should say we are studying that question. My guess would be yes, but I can't support that. Okay. In amplitude amplification, like the Grove's algorithm, it turns out that if you use quantum simulation logic, the first of the two models I showed you here, quantum simulation logic gives you a speed up which compared to a classical algorithm, but it's not quadratic. You get a logarithmic speed up. And right. I could explain why, but it's in the one of the papers. Yeah.
Then we have two more questions from another student, Jed. He's saying, since the Speckens toy model is efficiently simulatable classically and can be used to run the Deutsch-Jozsa algorithm, wouldn't this naively suggest the problem is solvable classically with order 1 queries?
It cut now, so I didn't hear the whole thing.
Let me repeat. Since the Speckens toy model is efficiently simulatable classically and can be used to run the Deutsch-Jozsa algorithm, wouldn't this naively suggest that the problem is solvable classically with order 1 queries? Since we know that classically it's still order n queries, what explanation resolves the paradox?
That.
Have we lost Jan-Åke or?
Yeah, I couldn't hear at all what you were saying.
Okay, I will repeat it one last time. Can you hear me?
Let's try again.
Since the Speckens toy model is efficiently simulatable classically, yes, and can be used to run the Deutsch-Jozsa algorithm, wouldn't this naively suggest the problem is solvable classically with order 1 queries? But since we know that classically takes order n queries, what resolves this paradox? Can you hear me, Hugo?
I can, yeah. It's definitely not on your side that there's a connection issue.
Okay. I think we might unfortunately have lost. Okay. Let's wait 1 more minute and see. I don't know how much bandwidth the green screen share takes up.
Right. Okay.
I think we've officially lost Jan-Åke, but Jed, I will make sure that we ask Jan-Åke this question after the seminar. I think for everyone who's still on the call, thanks for coming. Hugo's going to upload the talk on YouTube, so if any of your friends had to leave early, please let them know that the talk will be accessible. And we'll see all of you next week